Hello, everybody. Thanks for coming to the talk, and thanks for the introduction from Shiza. Actually, our kind of connection goes way back, right? So it was the first time, I don't remember the year, but 2016. We met each other back in 2016, and it was a math camp at Tsinghua University. Oh, at MOP. But then, and then in 2019, Shiza come to China. That was the first time that he visited China, and it was actually surprising to me that he stayed, and now he's hosting this fantastic event for the third time. And for me, it's a great pleasure to come to this event, and for this talk, I want to just talk about a research problem. Okay, and the research problem concerns the coverings of hypercubes. Here's what I mean. Okay, so you have a bunch of hyperplanes, and let's call them H1 Hm in Rn. Okay, and what we know about these hyperplanes is that they all avoid the origin, okay, and they cover all the other 2 to the n minus 1 points in the cube 0, 1 to the n. Okay, probably you have seen this problem last week. Okay. What I want to say is that, then there is a lower bound on the number of hyperplanes. Okay, what is that? Huh? What is the lower bound? M is at least. What's the minimum number of hyperplanes? By the way, is it okay if I use the word hyperplane in this context? Do people understand what I mean by hyperplanes? I mean a linear equations. So let's say that here in Rn we use coordinates x1 through xn to describe the coordinates, and a hyperplane is just an equation of the form a1x1 plus plus anxn is equal to b. Does this make sense? Hyperplane. Does this make sense? Okay. What's the lower bound? What do you think is a good lower bound for plausible lower bound for the number of hyperplanes that covers? Huh? Who said that? Raise your hand. Okay. Can you say it out loud? What is the lower bound? N or M? N. Okay, good. And why is that the reason? Why do you guess it's N?
Because the hyperplanes x1 plus x2 plus blah 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 plus Sn equals 1, 2, 3, 4 blah blah blah
Okay.
and
Okay. Yeah. Very good. Very good. So, by the way, what's your name? What's your name?
Zhe
Jagyo. Okay. Jagyo said that the reason to guess the lower a good lower bound on the number of hyperplanes is n is because of the following construction, right? We think about the following construction: x1 equals 1, x2 equals 1, xn equals 1. You see that each equation describes a hyperplane that avoids origin, right? the 0, 0, 0, this origin is not on any of these hyperplanes, but they together cover all the other 2 to the n minus 1 points in the hypercube, 0, 1 to the n. Does this make sense? Okay, so that shows you that you can certainly do this problem with n hyperplanes. And that's a plausible lower bound. Okay? How do you prove the lower bound? Any taker? I mean, yeah, here.
I think we can just repeat the solution for problem from last week.
Yes, exactly, right.
With polynomials. So with hyperplanes, no, with multiplied hyperplanes and
yes, yes.
Polynomials just for each point.
Okay, yeah, very good. So the idea is that it's just a special case of problem 6 from 2007, the IMO 2007 problem 6. Okay, and it's a special case, as you can see. Okay, so you go back to the problem, and this is a special case. Okay. Okay. Maybe not exactly a special case, but you know the problem is similar. Okay, and so the technique transfers, and this question is known as a long field ready theorem. It dates back to 1993. Okay, so somehow after 14 years, somebody on the IMO committee realized that they can take that problem and put it on IMO. Okay. By the way, Alon is a great figure in combinatorics, and he won the 2024 Wolf Prize, a very prestigious prize in mathematics. Okay, so there is this very nice theorem. So I'm going to today the goal is to present to you a research problem. Okay, that's a variation of this question. Okay, so what if every point in the hypercube, but the origin is covered twice. Okay. Sorry, I'm not saying that this is a research problem, but later I will further generalize it. So what do you think? If I want to cover every point twice, okay, what do you think is the minimal number of hyperplanes needed to do that? I still want to avoid the origin. Okay? I want to completely avoid the origin. However, I want to cover the other each of the other 2 to the n minus 1 points at least twice. Yes, it's that. Huh? N plus, okay, very nice. So there's a suggestion for n plus 1 hyperplanes. Okay. Usually, when I ask this question, people would say, 2n planes, because you can certainly double every plane here to cover. Okay, so what's the idea for n plus 1 hyperplanes? Okay, that's good, right? So you see that when we look at these hyperplanes, for example, the point 1, 1, 0, 0, 0, 0, 0, this point is already covered twice. by all of these hyperplanes, right? It's covered by x1 equals 1 once, and x2 equals 1 once, okay? So the only points that are not covered twice by this construction is the point where there's exactly 1, 1 in the coordinates. So for example, like 1, 0, 0, 0, okay? So let's observe that points 1, 0, 0, 0, 1, 0, and so on are covered by these hyperplanes, this collection of hyperplanes, only once. Okay, so in order, all you need to do is to cover these endpoints one more time, so that now every point is covered at least twice. And therefore, the suggestion was to add this one more hyperplane. Okay. And together you have n plus 1 hyperplanes that cover every point in the hypercube, but the origin at least twice. Okay. Are we okay with the constructions? Any question about the construction? Okay. Okay. Now you ask, is it possible to do better? Right. So we have a construction with n plus 1 hyperplanes, and you wonder if you can do better than n plus 1 hyperplanes. Right? So maybe something magical would happen to say that maybe it's still possible to have just n hyperplanes that cover every point twice. Okay. Yeah. Well, what do you think? Is it possible to still use n hyperplanes to cover every point except the origin twice in the hypercube? Yeah, I claim it doesn't, the argument doesn't, okay. The argument doesn't require, any machinery, right? Just, try to think. So suppose I have a set of hyperplanes h1 through hm that covers, all these points at least twice. What happens if I take away one of the hyperplanes? What happens? Huh? Okay, suppose H1, HM cover every point in the hypercube, but the origin at least twice, right? What can we say about, let's say, the first m minus 1 hyperplanes? Yeah, please. Yeah, it covers.
It covers each of points of hypercube at least one.
Yeah, and the
one
reason
time.
is that the last
And
hyperplane.
Yeah, it cannot cover some points twice.
Twice, right? So, right? Okay. So the last hyperplane cover a point in the hypercube at least once. So if you take that away, the rest of the hyperplanes still cover every point in this hypercube without the origin. Does that make sense? Okay, so you can reduce it to the first problem. Right. In that way, you know that m minus 1 is at least n, therefore m is at least n plus 1. Okay? So we have a construction that uses exactly n plus 1 hyperplanes, and we have a proof that you need at least n plus 1 hyperplanes. So the optimal answer is n plus 1 hyperplanes. Okay, so this problem is solved again. Okay, if you want to cover the hypercube without the origin at least twice, the answer is n plus 1. Okay? What do you do next? If math is about generalization, what do you do next? Yeah? K times, right? You want to cover every point in this at least k times. Okay, so let's define f and k to be the minimum number of hyperplanes avoiding the origin that cover the hypercube without the origin at least k times. Okay? And what we have shown is that f n1 is equal to n, f n2 is equal to n plus 1. Okay? What do you think we can say about f and k in general? I'm not saying that you should be able to write down inequality, but let's try to give upper and lower bound. Very good, right? Lower bound is n plus k minus 1. And the reason is that, if you cover all the points at least k times, you take away k minus 1 hyperplanes. And the rest of the hyperplanes should still cover all these points. Hence, by result on fn1, it's at least n. So the total number of hyperplanes need to be at least n plus k minus 1. Does that make sense? Okay, same logic. Okay, and as for upper bound, it's a variation of this argument. So you want to, for the upper bound, let me just write it on the side. You want to add this hyperplane k minus 1 times. And then this hyperplane, equals to k minus 2 times. And so we add on top of these basic hyperplanes. Okay? So these hyperplanes are always there. Okay? But on top of that, we want to add the following hyperplanes. So x1, xn equals k minus 1 at one time, okay, or once. Okay? So in total, we've added half of k times k minus 1. And you can check, this construction works. Okay? So that's the, if you really want to generalize the construction, this is what you get for the upper bound. So that tells us that already when k is equal to 3, lower bound is n plus 2, and the upper bound is n plus 3. Okay? And there is a gap. But this is already solved. Okay? So it is known, it's solved by Clifton and Huang. I think maybe it was in 2020. It was published in 2020. Probably solved earlier that fn3 is n plus 3. The upper bound is correct. Okay? And the technique they used is a variation of combinatorial national sets. So remember that for the along Furedi theorem and also for in last week's talk, Ben Yang told you about this combinatorial national sets. Right? And here, Clifton and Huang developed something called punctured combinatorial national sets. Yeah, the most difficult part of this combinatorial national sets is to spell national sets. I don't know if I spell it correctly, but I'm trying my best. Okay, and it's some improved. It's some sophisticated, slightly more sophisticated version of combinatorial national sets that can give you this fn3. So the next open problem is fn4. Okay, and from this result we know that it's between n plus 3 and n plus 6. Okay? And it's still not determined. Okay. And here's a question that all of us can understand, and it really leads to some really interesting mathematics, and somehow it's connected to the IMO problem 6 from 2007. Okay, and that's all I want to talk about. Thank you.
Let's thank Zilin for a wonderful talk. All right, questions, please.
Did someone dare to conjecture like the general answer?
Yeah, so in the paper of Clifton and Huang, they conjecture actually the upper bound is the truth.
For every k.
Not for every k, but you also need that n to be large. So for every fixed k, where n is large enough, the upper bound is the truth. So that's a conjecture. So you can say here, when n is, say, 1 billion, okay, just be generous, we expect that this is going to be n plus 6. Yeah, very good question.
Other questions, please. Please raise your hand if you have questions.
Is there any simple solution for the first problem you said? We have the upper bound, we have an example of n hyperplanes, but we didn't prove that we need n hyperplanes at least.
Yeah, that was done in last, okay, it was not exactly done last week, but the IMO last week Ben talk about IMO 2007 problem 6. And the technique can be used here to prove a lower bound. Okay, so
Yes.
I think, I will leave it as an exercise for you to think about. Yeah, okay?
Thank you.
Other questions, please. Raise your hand so I can see you. No more questions? Okay, if there are no more questions, let's thank Zilin again.